So let me now talk about a numerical technique to solve the Euler equations. And I want to start out with one quite popular technique in astronomy, and it's popular for good reasons, because it's popular by due to its flexibility and comparatively simple structure, and that is smooth particle hydrodynamics. And I want to tell you now a little bit about this. So we have already seen that what the Lagrangian equations of motion are, and SPH is a Lagrangian technique which works directly with these equations. And basically, when you want to numerically now simulate fluid flow, you need to discretize the fluid somehow. And there are two fundamentally different approaches for this. One is the traditional one, where you discretize space typically into cells of some size, or some finite elements that are stationary. And those elements are usually a grid or a mesh. And then a corresponding description is called Eulerian hydrodynamics. And we also saw the Eulerian equations. Here you work basically in a real space, and you're not describing the equations of fluid flow along the motion itself, but stationary at fixed coordinates. We'll see tomorrow a lot more about Eulerian techniques. They are mathematically trickier because they try to solve the partial differential equations directly that the Euler system represents. And solving partial differential equations is mathematically, in general, a relatively involved field. In smooth particle dynamics, we try to discretize the fluid differently. We try to represent it by mass particles. We present the fluid intuitively by a few points, and they stream through space, and that will be our fluid. And that description is also very similar, of course, to what we've done with the dark matter. We discretize in terms of particles, so there is a close analogy there. The principal advantage of this description is also clearly that if, say, a cloud of gas decides to go into collapse, the points will move together, get closer together, and that will directly mean that your spatial resolution in your flow will improve. That's an advantage that is very convenient for these techniques, especially in the applications to cosmic structure formation, because we have collapse over large factors, and as we saw with the particle mesh technique, a uniform grid is completely inadequate to cover this dynamic range. It's not efficient for it, it's not made for it. But if you follow the mass along in this Lagrangian nature, you are also not restricted in the geometry, and there's no intrinsic limitation there for the dynamic range you could potentially cover with that. So that makes, right from the start, the SPH technique that we'll now look into very attractive. So one of the fundamental things that SPH uses is the concept of adaptive kernel estimation. And that's a technique to construct interpolants from a set of discrete points only. And the concept starts essentially with a kernel interpolant of some arbitrary function a here. Suppose I have a function a of r, and then I convolve it with this sort of smoothing kernel here, w. And the smoothing kernel has some characteristic size h, which is my smoothing length. And in this form, this equation is just a convolution. I'm washing out this function with this smoothing kernel. And the smoothing kernel can be something generically we would expect we'll use something like a Gaussian, more or less, from the shape. And there are different possibilities for these kernels, but where often in SPH is a simple spline, or nowadays in the newest developments also somewhat higher order kernel functions are used, more involved splines, but they generally have shapes like this. Okay, so now it's clear with this you will just wash out small features in this function and get a smooth estimate. Now the idea for SPH is now to use that concept to try to make an estimate for this smoothing integral by basically a Monte Carlo integration technique. you say, okay, suppose I know this function a of r prime only at a few discrete points. Here are my points, and you put down your kernel, which has a finite support, and that's now here indicated with the circle of radius h of I. And now I would like to estimate this kernel interpolant here, this smoothed function, by a Monte Carlo integration. What do I have to do for this? Well, I replace the volume element here, dr prime, with an estimate of the volume covered by every particle. And that is m over rho. Okay, is the differential volume associated with a particle. If I know its density and its mass, I can then estimate its specific volume. And this you replace here in the differential. You cast this integral into a finite sum, and you end up with a formula like this. So now it's a summation, and it's basically, you think that this is appearing by basically a Monte Carlo integration of this, where you take these support points here and their differential volumes, and then you get an approximation to what you expect for this smoothed function. So and that's indeed the SPDH kernel interpolant, the basic machinery that's used in SPH to construct from a set of discrete points what in other fields of fluid dynamics you would call a reconstruction. You now have something that is basically in principle there everywhere in space. You can extend that interpolation to every coordinate, and so you can extend the function a that you now know only at the points to all of space with this formula. You're interpolating between these points. That's called a kernel interpolant. And this directly leads to the SPH density estimate, because one problem here is that if you look at this formula, for example, if you want to use this to estimate the density, then it turns out, well, you don't know the density A yet. But in the lucky case of the density, you see if I want to estimate the smooth density, you make A the density, then the rho j cancels here. That means the density estimate is simply the sum over the masses times these kernels. And I should say the kernel here is, the smoothing kernel is normalized to unity, right? So if you integrate under it, you get 1. So that's the formula for the density estimate. And the additional thing is, if you now do this extension to arbitrary coordinates, you have now here the density at a coordinate of the particle I, but I could also take a coordinate in between the points. And in other words, I have a whole density field here that I can estimate from the particles. And this density field can also be differentiated. Even though I've only a set of points, I can now construct differentiable fluid quantities. And the differential operator will act, if I apply that here on this formula, it will act on the W. So what I really differentiate is the kernel. So the kernel needs to be differentiable. So here are some conditions on the kernel. Must be normalized to unity. It is better if it has compact support. This is not a strict must, but if it has compact support, this means the number of neighbors around your point is finite. And it's not equal to the whole number of points you have in total, right? But it's a much smaller number normally, and that makes it computationally tractable. If you would not have a compact support, that would mean infinite support, right? Then you would always have all particles appearing in the sum. And then evaluating something like the density for all particles would be an n-squared process. And we have seen how deadly this is for large particle numbers. So you better have a compact support. It is good if it has a high order of interpolation, and spherical symmetry is also needed for angular momentum conservation, for example. Nowadays, well, this is not true anymore. This unfortunately is an old slide. I stated here almost exclusively the cubic spline is used. Actually, recently there were new kernels suggested, for example, the Wendland kernels by Walter Denel, and they are becoming now popular. So I think it's not true anymore. SPH is in the process of probably adopting higher order kernels of some kind, for the most part. So now how do we then look at the other Euler equations? To complete SPH, we not only need a density estimate, we need equation of motions chiefly. To get them, I mean, we can first of all look at smooth estimates for the velocity field, do that like the density. So you can use this kernel independent formula to, for example, get an average velocity. You can use it now in the differentiate case to get something like a divergence of the velocity. Again, with the kernel interpollant formula, you would do it like this. But there are multiple ways to often to estimate such quantities. For example, instead of using this discrete formula for the velocity divergence, you could first invoke the identity, this simple product rule identity for the combination of density and velocity. And using this, you can also derive a pairwise formula, a pairwise estimator for the velocity divergence of particle I in this form, where for all your neighbors, you multiply the velocity difference into the gradient of the kernel. And this is sort of one of the rules of wisdom in SPH. If you use sort of pairwise estimators like this, you usually get better results, not in all cases. And here we see for the first time one of the nasty aspects of numerical implementations. There are often multiple possibilities, like here. You know, I have two possibilities to estimate in SPH the velocity divergence, this one and this one. Both seem perfectly viable. Which one is better? You can often not tell easily just by equations like this. You can't tell. You have to, if you don't discover a good reason from a mathematical point of view, you have to find this out by trial and error and experiment with it. So yeah, so this is sort of experimental programming then sometimes, what you have to do at some level. Now the density estimate is directly fulfilling for us the continuity equation. If we put down mass points and just let them move around, mass is obviously conserved. And so indeed, the continuity equation is something we don't even explicitly have to calculate in SPH, just solved automatically. That's nice. And so we only have then also the pressure equation. We can always update the pressure, of course, with the current densities that we estimate with this formula. And then for the Euler equation, we can try to discretize with formula like we saw on the previous chart, the gradient operator on the pressure over the density. And then, for example, we can derive an equation like this for the equation of motion. So this would be, so the traditional SPH equation of motion is exactly this. And here already there are, different possibilities, like for the velocity divergence. I don't want to list them all here. In particular, what I also have just indicated here is if you look at the gradient here of the kernel, there's now suddenly an index ij here and an overline. And that overline is meaning that some form of averaged kernel is used here, or symmetrized kernel, because in practice, one makes this smoothing length hi usually a function of the particle I itself. So every particle has its own smoothing length, and it's allowed to shrink dynamically if, for example, the gas particles cluster. So that's generically done. Otherwise, you cannot really exploit the adaptivity of SPH. You have individual smoothing length, and that invokes the problem that if two particles interact in a pair, what smoothing length should I pick? If two particles I and j interact, should I pick the smoothing length of I? Should I pick the smoothing length of j? If in the fourth equation you would pick the smoothing length of I for using it for particle I, but then for j you use the smoothing length j, which may be different, you'll see that the force antisymmetry would be broken. That's very bad, because that would mean that the particle pair could propel itself into infinity, right? If they exert a net force onto each other, they could violate momentum conservation really badly. So you want to have force antisymmetry. And this is normally achieved in the light of adaptive smoothing by symmetrizing either the pressure terms, you symmetrize the kernels or you symmetrize the smoothing length. And then the first law of thermodynamics is stated here. This is now the work term against the pressure in this form. So there you go. This is basically SPH. Well, it's not complete yet, but more or less we have now these two equations that we have to solve. And we'll see actually that this equation can also be avoided. If we go to a formulation which uses the entropy instead of the thermal energy per unit mass, then we don't even need to evaluate the thermal energy equation at all. And since the entropy is constant, we effectively don't have to evaluate this either. Then in SPH you only have the equation of motion for the whole gas dynamics. And that's a huge simplification compared to the set of partial differential equations that you saw in the Eulerian form. So that makes this very simple and convenient. But I forgot one important point that comes up now, as we previously saw early in the morning. That the Euler equations are in a sense incomplete in the differential form at least, because they maintain in smooth parts of the flow where these differential forms are valid. The entropy is constant. And we also saw that at shocks this is not true anymore. So discontinuities will develop. And so in this differential form, we somehow need to have a mechanism to account for the injection of entropy at the right place. And that can only be done in SPH by now putting in an artificial viscosity, which is put into here, into these brackets, the artificial viscosity tensor, capital pi. And this is very similar. This is basically has the same sort of effect and action as the physical viscosity Navier-Stokes equations. Except that it's now called artificial because, well, we don't have a real viscosity in a Eulerian, in an ideal gas flow. We don't have a real viscosity. But we want a viscous tensor here to be present, nevertheless. But ideally, it should only be present right where a shock is, basically. So this is going to be the challenge, to make an artificial viscosity that somehow auto-detects when the fluid develops a shock and then provides some viscosity that will capture the shock. That's what one says, right? Renders it not into a true discontinuity, but in a short transition between two different states of the fluid, which are then themselves again smooth and non-viscous. So the viscosity in shock capturing is very important. I showed you the a typical SOT shock tube before. Here you see, probably only the people in the front row can see this, the density initially in the SOT shock tube test that we had. And then this is the evolved state, how the density evolves. And here the velocity was initial 0 everywhere. And now it developed this shock to the right side that propagates with some velocity to the right side. And then also the entropy was piecewise constant. It had on the right this level, on the left this level of unity, and the pressure was up here and it was down there. Now, the real evolution of this problem will create this two-step feature here in the rarefaction wave where the gas is expanded. So here you have the very left side, the gas is still unperturbed. The very right side is still unperturbed. And that's the case in all of these panels. Then we have the shock traveling to the right. And the shock in the specific entropy, you see now that the entropy jumps at the shock. That's exactly the entropy production here, right? So the gas on the right that used to be on the right-hand side here is, by the shock, its entropy is increased. It is accelerated because it's then have a certain velocity. And it's also compressed because its density increases. That happens at the shock. And at the contact discontinuity, which is behind the shock, you see that only the density jumps, the velocity is now continuous, pressure is continuous, and also the entropy will jump, as also the temperature does. And with blue symbols, you see that an SPH result for this problem. And broadly speaking, the SPH reproduces these features. In particular, you see here that there is an entropy production here. Okay? And this entropy production can only be present in SPH if you have an artificial viscosity. How does this then work? Well, you need to put in a viscous force. This is this part that we had in the equation of motion. The viscous force itself is just added to the ordinary pressure forces like this. And the artificial viscosity tensor, this is, for example, one parameterization of this, which uses a kind of a switch, which is here this quantity W, which measures the rate of expansion, the rate of expansion or contraction in sort of units of the sound speed. And if this is large, so if the gases particles approach each other on a short time scale relative to the sound crossing time over their distance, then this viscosity tensor says, oh, oops, there is a rapid compression, I better be viscous now, okay? And if there's an expansion, then this switch gives you zero viscosity here. So you can, and this is also black magic, what you use here. This is sort of not really constrained. You're trying to somehow come up with something that will detect rapid compressions leading to a shock. And ideally, it should only be there that the viscosity is active. But once you have the viscosity, then you also need to produce heat with it. Okay? The heat production rate is directly proportional to the viscous tensor, to the work you do against it. So whatever you do against the viscosity is produced into heat and is irreversibly lost in the system. This is directly also producing entropy. So now I want to show you that traditionally the critique of SPH was often formulated in the case, was often like, oh, SPH cannot do shocks. I think this is really far from the truth. SPH can do shocks really well. It produces the correct post-shock flow, post-shock properties, and it injects the right amount of viscosity, the right amount of viscosity, entropy, I meant. So SPH injects the right amount of entropy at a shock, and the properties of the post-shock flow are correct, and they agree with what the Rankine-Huguenot jump conditions say. And the reason for this is ultimately because SPH is fulfilling the conservation laws accurately. You saw that the jump conditions arise from the fact that momentum and energy must be continuous or conserved across a shock, and also mass. And that's fulfilled by SPH, and that's ultimately why the jump conditions will also be fulfilled. Here in this little movie, I just showed you that this is a strong Mach number 10 shock overrunning a cloud that was initially in pressure equilibrium. So there was a cloud sitting here, which was a factor 5 or so denser than the background at pressure equilibrium, and then this Mach number 10 shock is running over it, compressing it, and there are lots of strong shocks and relatively complicated fluid phenomena occurring. There's some vorticity created by the baroclinic term, and that sort of all works at some level in SPH. I say at some level because there are also some interesting features that you see here, that these little remainders from this compressed sphere here, there are some little droplets that are spun off, and they swim now in the fluid without being further mixed away. And we'll see later why this is. Okay, you see here some issues. So the problems of SPH, if there are any, are not in the shock. They are more in the mixing, maybe, and in the fluid instability sector, as we'll see. So before I get to this, I want to mention that there is another way to. So far, I sort of played just with sort of an ad hoc derivation of the SPH equations. We just stare at possible differential formula that you find a difference formula that you could use, and you find that there are many different possibilities, and you then have to try all of them against each other and try to understand which one is maybe the best formulation. And that has been done for a long time in SPH. But there are also variational formulations that are now much more popular. And the variation formulations they start, for example, I mean, I find it convenient to use the entropy, but it's not necessarily required that you use the entropy. So the entropic function we saw before is related to the pressure in this way. Pressure is entropic function times density to the gamma. And for an adiabatic flow, this A is only a function of thermodynamic entropy per unit mass. So then thermal energy, entropy are related like this. And you can, instead of invoking the thermal energy to describe viscous heating, you can use now the entropy. And you see, previously, this whole expression was the viscous heat generated in a shock. And it's also directly generating entropy in a shock. So the entropy only evolves due to viscosity now. Okay, that's the nice thing. While the thermal energy evolves also due to adiabatic compressions and expansions. Entropy is therefore a quantity that only evolves due to viscous heating, and the change is positive definite. So the entropy can only go up. Okay, can only go up all the time. Unless you have radiative cooling, this can make it go the other direction as well. But that's basically a source term that externally is added to the simple equations. Then originally, it was well known in SPH for a long time that if you have these two choices, if you integrate the thermal energy, if you pick this as your independent variable, you'll find that sometimes entropy conservation is violated. If you pick instead the entropy and basically use this and write down SPH equations for them, the sort of canonical ones, then you find out that energy conservation is sometimes violated. And the question is this generic, or can you have conservation in both? And the origin of these problems are lying in these variable smoothing lengths, because those are sort of arbitrarily adjusted in more or less uncontrolled way, and there are, strictly speaking, also so-called grad H terms that should enter the equation of motion are normally neglected because they're too complicated to algebraically derive and then also messy to code up, so they're usually neglected. That was the origin of state of affairs, say 10 years back, that one had this sort of situation, and then in this case, most people would now pick the total energy as thermal energy as integration variable, because who looks at the entropy anyway, right? This is violated. That is, yes, I mean, it's basically like this, right? Energy conservation is clear to everybody, but entropy, what was this again, right? An entropy violation here means that somewhere the entropy is going down, but that's not allowed, right? It should not go down if they don't have cooling in. So you then close your eyes and better not look at this, right? But there is a better choice, and it's basically, you can derive this from a Lagrangian or Hamiltonian. You look at the fluid Hamiltonian or fluid Lagrangian, which is basically the kinetic energy of the flow minus here the thermal energy. Or the fluid Hamiltonian would just be kinetic energy plus the thermal energy part. And then you derive your equation of motion using the techniques of classical mechanics. You derive Hamiltonian Lagrangian equation of motion from it. Subject now, and that is what you can put in. You put in a constraint that you now say how you want to pick your smoothing length. And that's the new thing that was needed in SPH, that you say how precisely do you want to pick your smoothing length. For example, you can use an equation like this, that you say, okay, in a certain volume around my point, 4 pi h cubed over 3 is my kernel volume, multiplied times the density should be some fixed multiple of the particle mass, some constant mass. That would say, this sort of equation says you try to maintain a constant mass inside the kernel. And this condition then tells you how you have to set your smoothing length. But notice this is an implicit equation, really, because the density that appears here is itself a function of the smoothing length, right? So you have to find the root of this equation. But this is actually can be done efficiently in SPH algorithms, so I don't want to discuss this more. So you have the Euler equations from classical mechanics, and then you derive this equation of motion. And now you see, oops, looks a bit different from before, because previously we had these two pressure terms, pi over rho I squared and pj over rho j squared. We had them together, and the symmetrized kernels were outside of this bracket. And now you see that they are paired up. And turns out, yes, this equation of motion now simultaneously conserves energy and momentum. So with this, we then obtain indeed more accurate results. And that also shows up in practice. I don't want to actually very much talk about this, but just I think it's probably sufficient to say that this equation of motion is now more or less used by almost everybody in the field, because it just creates slightly better results than any of the alternatives. Okay, so what else do I want to say about SPH? Yeah, I guess a little bit about some of the technical things. The neighbor searching is if you now want to program these equations and write a little hydrodynamical code. The one routine that will give you trouble in SPH, all the rest is really simple. But the one algorithmic aspect that will also govern how fast your SPH code is actually the SPH neighbor search. Because you saw that you have to do these sums over neighbors all the time. The individual terms are simple to calculate, but what is not so simple is to find efficiently the neighboring particles that you want. If you just do a loop over all particles and filter out those that are in your smoothing region, then you'll have again an n-squared algorithm, right? So somehow you need a much faster method to selectively find among all the particles those that are in your smoothing region. And for that, basically, you need an efficient neighbor search. And here, this is very often done with tree algorithms again. In fact, you can reuse the same tree that you maybe have used for gravitational tree calculation. And a neighbor search then in such a tree proceeds like this. So for example, suppose you want to have the neighbors around this guy up there in this sphere. And then you look at the root node, you compare the root node with this sphere, and say, oops, there's an overlap, spatial overlap, which you can test really quickly. That means, potentially in this tree there are particles in my sphere. That means you now need to look at the daughter nodes. You need to open this node and look at it. But you now only need to look at 2 of the daughter nodes, because only those have a spatial overlap with your smoothing region. And that means basically you will, for example, from this point onwards, you'll never have to look at anything here. Right? These are already gone. And then you go further, you open this because you had an overlap. You come to these nodes. They have an overlap. You have to open them as well. And eventually you get down to these nodes that contain your target particles. And that is a tree walk, right? Similarly to the one that we do for gravity. And with this, you can very rapidly, in a cost of order log n, find the neighbors that are inside this region. It's a spatial search. That we have to use. There's a small complication. You actually have to, in the equation of motion, you need to have a more complicated search that's able to, because you only know maybe the smoothing length of your particle hi, but you actually want to find all the particles that themselves overlap with you within their smoothing length. That's more complicated. You can do this by storing in every node the maximum of all the smoothing lengths that appears among all the particles inside the node. So let me now make some comments about the nice and good things about SPH, and then about the bad things of SPH. So what SPH is really good at is in its conservation properties. Mass is conserved trivially, okay? With constant particle masses. Momentum is conserved. Total energy is conserved. That's also the case to machine precision in principle in the case of self-gravity, which is much harder in a mesh code to. Normally you do not have manifest conservation in a mesh code for once you have self-gravity for total energy. Angular momentum is also conserved. Same thing here. In a Cartesian mesh code, normally you will have not manifest conservation of angular momentum. And also entropy is also conserved. In fact, you have complete control about where entropy should be created, you know, via the artificial viscosity. So this combination of this complete fulfillment basically of all the conservation laws is kind of unique to SPH. And furthermore, you have high geometric flexibility, easy boundary condition treatment, no high Mach number problem. That means it's Galilean invariant actually, and you have no problems in highly supersonic flow to pick up weak shocks, for example. But there are fundamental issues in SPH, and they come from two areas. One, and that basically what the problem is, that it's not an overly accurate technique. One problem relates to the viscosity. You saw that if the artificial viscosity is coming sort of in an ad hoc fashion into the scheme, then very often it will be the case that the viscosity is somewhere higher than it should be or is needed, and it can also be lower than needed. If it's lower than needed, you, for example, get post-shock oscillations that can be quite strong. If it's higher than needed, you get entropy production in the wrong place. You get damping of sound waves and all crap like that. So that's a problem, but there are more serious ones even. And one serious one, and that has been discussed a lot in the literature, is Kelvin-Helmholtz instabilities and fluid instabilities that don't want to grow very well in SPH often. This is a test example from this paper by Agertz, where sort of the test that we've done yesterday in the hands-on session, more or less, is repeated, and in two different grid codes, you get these Kelvin-Helmholtz billows developing, and in SPH over the same time frame, nothing happened. And now in this case, we kind of know, because of the linear growth analysis, that this perturbation should have grown, but it didn't. And so then we know that this is actually the more physical result. So it's really wrong in SPH here. And we would like to understand why this is. Now, there are different reasons for this actually. One has to do with accuracy of gradients in the interface. But there's also a substantial obstacle in SPH due to preventing mixing basically of the fluid elements, which is by construction basically absent. You can look at a little toy Duncan experiment if you want. And let's look at this little box filled with SPH particles. And there are two halves in there. Here the density is, say, 8 on the left, and on the right it's 1. And then the temperature is 1/8 here and 1 on the right. So that means that the pressure will be equal in both halves. And they are also filling half of the volume, which is a unit volume here. So the pressure is equal. This is a contact discontinuity. Nothing happens here. We can calculate some quantities. The pressure is, as I said, is constant. It's 2/3 here on both sides. The specific entropies we can also calculate. This is on the left side. This is pressure over rho to the gamma. It's 1/48th on the left and 2/3 on the right. Equipped with this, we can also calculate the total thermal energy of the system. This would be, can be done in different ways, but would be basically the integral over this quantity, the thermal energy per unit mass, times the mass. And if you do this, you get 1. So far so good. Where is the problem here? There's no problem here, in fact. Problem starts if you imagine, let's take these particles as they are and drag them around, put them down at different places, and we put them down such that they are completely mixed, so that they're all at different places and nicely uniform as far as I can do that. So I put them down like this in a mixed state. Now let's think, okay, what will be the density now? Well, that's simple enough. All particles will estimate now the same density. Must be 9/2, right? Because I have the mass was constant in the box. I didn't put any new particles in and out. So every particle will now see around itself a fair mixture of these two species. and so we'll estimate the density to be 9/2. And then you now can calculate the thermal energy again that you now expect. And the thermal energy we'll calculate exactly like here, because the entropies, we didn't change the entropies of the particles, right? We left them as they were. They are conserved. So then we just add up from the entropy and the density, you get the thermal energy times the mass. You add up the new thermal energy. And what you get is 1.7. And now you should be surprised. What has been going on here, right? The thermal energy is now larger than it was in the beginning. Well, that kind of means that this process will not happen by itself. It's energetically forbidden. It will not happen by itself. The two fluids can't mix. Okay? They don't want to mix because it's energetically forbidden. They could, however, if they decided to average their entropies, to exchange entropies, and for example, by thermal conduction, they have different temperatures. If they decided, oh, let me do a lot of thermal conduction so that the temperatures are equilibrated, that will mean the thermal conduction will keep the thermal energy constant. Okay? Then the entropies will be equilibrated. And then you'll find out that then a final state is possible where the density will be 9/2, the energy is 1, and everybody has the same specific entropy, but the total entropy then is actually larger than it used to be before. And this additional entropy is the mixing entropy that is not included in the normal equations in SPH. Right? That's why modern SPH schemes, they try to fix this by adding artificial mixing, artificial heat conduction. And that comes in various flavors, and that's under very active debate how you can do this. So I'm almost out of time. I think this is one of the crucial points in SPH. You need to allow some mixing. You cannot live with the complete suppression of that. And there are solutions discussed to this. The other problem that is still, even after you fix this, still remains is the issue of the accuracy of the gradients themselves that you estimate from the kernel interpolation. Because these gradients are rather noisy, and this noise is can only be beaten down by using more neighbors in SPH and higher order kernels. And that makes the technique also fairly expensive now. So currently in the literature, people discuss kernel numbers up to several hundred in order to get SPH more accurate. And in this case, you can, here's this, what I just described to you with the entropy, that the entropy needs to increase in order to allow this mixing. So I'm actually at the end of my time. And I just want to say that some progress has been made on these problems. So with these mixing in place, larger neighbor numbers, and sometimes then you also need usually another kernel if you use larger neighbor numbers. Then you can actually get the Kelvin-Helmholtz instability working, okay, in SPH. More or less. That's there are still issues with this noise and with the overall efficiency of the scheme, but I personally don't think that SPH is completely dead, but it's half dead in my view. So yeah, I leave it with this. So thanks a lot.
Okay, I think we can take 5 minutes for questions.
Yeah, 5 minutes for questions. I was supposed to end at 35, so I've done it. Any questions? Yes?
So I have a question about the mixing in the SPH code. So you mentioned if I want to do, for example, the supernova chemical enrichment in SPH, for example, gadgets. So I need to implement some mixing or diffusion recipe. But if I put many very high resolution, many particles, can it still do like the mixing automatically through those particles? Is it possible?
Yeah, well, I think what you mean is that if you increase the resolution so much to eventually get to a real physical situation where, in a way, in the ultimate limit, your SPH particle is like the individual chemical element, right? And I mean, the atoms themselves, there is, after all, an oxygen atom, and there will be nitrogen atom, and so on. And there's a coarseness in that at that level, at the atomic level, how things are mixed. And if you get that to that point, you would think SPH must go maybe to this limit in the large particle number limit, right? But I think whatever particle number you use in standard SPH, there will not be any change in how the mixing is done. You could only argue that maybe I should, so there will not be an SPH element will have, an SPH particle will have its chemical mixture that you can prescribe from say enrichment. You give it some chemical mix, and that chemical mix will always be maintained for this individual particle. And you can only then talk about mixing if you say, oh, I'm averaging maybe over some fixed spatial region, and then I'm counting how many particles and how many or how much mass I have of certain chemical elements, and then I can calculate the average chemical composition, and that's effectively mixed. So the question is, maybe this is good enough. I don't need to ensure that also all the individual particles have the same chemical mix now, right? And that, however, you could mock this up. If you decided that this is what's needed, you could have a artificial diffusion term, so that mixes this around on some scale. The reason why you might want to have that is because, we think that there is maybe on very small scales, eventually there is some non-negligible viscosity, especially say in the hot gas in the galaxy cluster. So any turbulent cascade that will be present that mixes it efficiently, and eventually it will be relatively uniformly mixed on below a certain scale. And then you have cooling also, and the cooling functions respond to the metallicity strongly. And if two particles are directly adjacent neighbors and have the same density and same temperature and so on, then you don't necessarily want that one of them is cooling like crazy because it has some metals and the other not, right? And so I think you cannot solve this problem just by increasing particle number.
I think about the SPH is bad at doing the mixing originally. I think it's about because it's bad at resolve the fluid instability and induce the mixing. So you need to have other different way to do the mixing. For example, using the diffusion.
Yeah, you can. You can do it, as I said, you said, with treating the mixing, you can then make the fluid instabilities work. I should also say I shouldn't be so negative about SPH because, whether or not this is a problem with the fluid instability very much depends on your problem, right? So of course, if you set up a problem that where you look at the Kelvin-Helmholtz instability in isolation and you don't see it, then obviously it's a problem. But there are many physical problems where maybe this instability doesn't play an important role, is irrelevant whether you treat this accurately or not, because doesn't even appear in any significant way. And so it depends on the application. For example, very strong supersonic flows. In supersonic turbulence, for example, SPH does quite well in reproducing the cascade you expect in supersonic turbulence when you dominate it by kinetic motion, not by pressure gradients. But the more subtle fluid phenomenon where you have weak shocks, weak fluid instabilities that are reacting sensitively to pressure gradients, their SPH is not really good because it's often there in the noise, right? But as I said, there are many applications where SPH works quite well. So I don't want to dismiss that at all for that, right? And you have to very carefully look, are you bitten by the accuracy problems in these fluid instabilities in your particular problem or not, right? And I think now there's a much higher awareness of that there are sometimes situations where the accuracy in SPH is not sufficient. And the problem is you don't necessarily realize this. Say in galaxy formation people and things like cold flow accretion of gas onto galaxies and so on, we noted that there are huge differences between SPH results and our mesh-based calculations, and we think they are mostly to blame on inaccuracy in SPH. And we wouldn't have known about this if we wouldn't have made a comparison between different techniques. Yes, there's a question.
Okay, so I'll bite too. Regarding SPH being half dead, I agree that there are certain cases where you might want to apply it, but it would be more suitable. But in general, you'd like to have a method that works in very broad context, right? Ideally. So my question is, do you think that things like pressure, entropy, SPH, changes to artificial viscosity or to the kernel, like Hopkins, Reed, Wolski, etc., are doing, do you think that these sort of revitalize SPH or put it on life support?
I think the verdict on this is still out. I mean, I'm obviously of biased opinion here. I think that these are interesting developments. I think currently that they get around some of the weaknesses in SPH. What is not addressed, I think, is that the accuracy of the gradients is not second order accurate, basically, and that is not solved in any of these fixes. And I think this will ultimately be a serious problem because it affects the convergence rate of SPH, of particle number. That means if you want to get real precision results, you have an inferior convergence rate in SPH always than in a mesh code. And what is good about SPH, it gives you a rather robust and qualitatively often correct result at fairly low particle number. But if you now want to go to very precise results, so for example, you increase your particle number by a factor of 10, you want to have 100 times more accurate result, second order convergence. That is not happening in SPH. You get only a relatively modest improvement in accuracy when you increase the particle number, and at a rate that is much slower than in a mesh code. And that's why I think until this problem is solved also, I would rather say it's on life support. It will be always good enough to infer qualitatively what's going on, maybe in many cases at low resolution, but for really precision work, it will not. I don't think currently the prospect is extremely good, but I mean, I'm happy to be convinced otherwise. Yeah.
Okay, I think we have to move on now. So first, let's thank Volker again.